Hypothalamus artificial intelligence. Presence. OPTEX, optimization expert system. The optimization technology that allows you to assemble multi-problem mathematical models like a Lego game, using structured mathematical modeling. Can you imagine how? Imagination is the beginning of creation. You imagine what you desire, you will what you imagine, and at last, you create what you will. The optimization expert system makes it easy to making high-complexity large-scale mathematical models without programming. The best way to make software is having to do it, is the goal of OPTEX. The high approach is aimed at developing cognitive robots that eliminate the tasks of computer programming, since the robot takes care of this process. This enhances the mathematical modeling capacity of the professionals. The traditional process of mathematical modeling implies that programmers, usually mathematical modelers or data scientists, must make great efforts to implement complex optimization models. Normalization and standardization, the base of mathematical programming 4.0. The foundations of OPTEX database algebraic languages consider the algebra as a standard, to express the relationships between the different parts that make up a mathematical problem. It can be said that there is only a reduced way to write an algebraic equation. This is independent of the symbols that are used to represent the physical or logical relations. Additionally, if two algebraic formulas are joined, a new algebraic equation is obtained that retains the same structural characteristics of the original equations. This transitivity law may be extended to mathematical programming, MP, which in essence is a collection of algebraic elements. Then it is possible to join two MP problems to obtain a new MP problem. It is also possible to divide an MP problem into two MP problems. Then, OPTEX can easily generate a new model as the addition of two or more MP models, or as a variation of an existing one. On the other side, it is practically impossible that the union of computer programs generates a new correct computer program. The principles of transitivity between MP models, formulated based on a database algebraic language, can be extended to more complex structures, such as those derived from the partitioning and decomposition of systems to apply large-scale optimization methodologies. In this way, the new vision of mathematical programming involves defining the relationships between problems, as the next step after the definition of the equations that compose them. Resuming, if the formulation of algebraic expressions is normalized, it is possible to have a standard way of representing a mathematical model that can be understood by another mathematical modeler, making it a standard for formulating MP problems. Additionally, the combination, or division, of MP problems generates new MP problems, which can be solved using many optimization technologies. Therefore, to facilitate the development of models, it is convenient to establish basic principles, norms or standards, of modeling, in order to enhance the use of models and ensure that they remain current over time, thanks to conceiving as a dynamic structure that adapts to changes in computer technologies. This implies, previously to the implementation of mathematical models, establishing a standardization manual that guarantees the understanding of the mathematical model, by any professional knowledgeable about the subject. This fact will result in the portability of mathematical models and the significant decrease in the implementation time. Structured mathematical modeling is similar to assembling mathematical models like a Lego. A mathematical model stored in an information system can be conceived as the union of mathematical components harmoniously integrated. There are two types of components, or objects: basic mathematical definitions, indexes, sets, parameters, and equations or constraints; advanced concepts, problems, models, decision support systems, and artificial hypothalamuses. These components can be stored in a relational information system. It permits their handling in a modular way. Following the principles of relational information systems, and use structured query language, SQL, to manipulate the mathematical objects. This conceptualization is independent of optimization technologies, which allows to separate the formulation of the mathematical models from their implementation, using a specific optimization technology. The nuclear unit, the molecule, of a MP problem is the constraint, which is the result of integrating various types of atoms. indexes, sets, parameters, and variables. Based on the constraints, more complex mathematical structures are built. Problems, sets of equations and/or set of subproblems, models, sets of problems and/or set of submodels, decision support system, set of models, and artificial hypothalamus. Considering that the problems are defined based on sets of constraints. If the modeler has built a database of equations, such as an equation store, he can formulate as many mathematical problems as the combinatorics of constraints that can be assembled. Traditionally, a problem is conceived as a monolithic set of equations. Under a modular conception, equations are components that can be shared by multiple problems. The important thing is that each equation works properly. This correct operation will be repeated in all the problems in which it is incorporated. If a store of equations exists, constructing a problem is limited to selecting the equations that make up the MP problem, and/or incorporate sub-problems that already have associated equations. This monolithic approach is easy to implement, however it does not allow the use of large-scale optimization methodologies. If it wants to use high-performance computing technologies, based on parallel processing, it needs to divide the mathematical model into multiple problems that represent the most elementary components of the physical system. This produces a significant gain in the solution time, and in the understanding of the inner operation of the system. To solve the model, it is necessary to select a large-scale optimization methodology that defines the processing of information in each problem. For example, the figure represents a mathematical problem related to the SAND-OP, sales and operations planning, that may be constructed based on 8 groups of equations. Production, energy, maintenance, distribution, sourcing, human resources, financial, and sales and marketing. The view the systems, groups of equations, that must be included in the SAND-OP problem depends on many factors, because there is no revealed truth regarding what the SAND-OP problem is. Since the equations are defined in a database, the configuration of a problem is limited to selecting from the equation store which are the ones that the modeler want to consider in the model. These visions can change within an organization. In this way, the modeler can have multiple SAND-OP models which depend on the use you want to give to the models. These models can exist permanently, or they can be created on the fly at the time they are required to be used. A decision support system must group all mathematical models, predictive and prescriptive, that uses the enterprise. Therefore, a DSS can be defined by the set of models that integrate it. Associated with the DSS must be the flow of information between the models, since it is logical that the output of one model is used as the input of another model. The traditional is that these models are used by users in a manual way, except in cases of advanced optimal control in which the models can run permanently, in real time, in an infinite cycle. An example of the architecture of a production DSS in an organization is presented below. It is made up of 8 models. The diagram describes the data flow between models. Traditionally, these models are run with a certain frequency, daily, weekly, bi-weekly, monthly, and the implementation of the decisions depends on the professionals who must validate the results. In some cases, this validation is automatic. The model's interconnection chain has no limits, which is necessary for an organization based on advanced analytics. The concept of model integration is applied in multiple dimensions. For example, an integrated oil company can be conceptualized based on the operation of 4 businesses: production, crude oil transport, refining, and transport of derivatives. In this case, the complete model of the company corresponds to the integration of the 4 models. For example, the figure represents a mathematical model for a multi-business enterprise that operates 3 business: electricity, oil and gas. The integrated model of the company will be the union of the 3 super-problems. However, the modularity of the modeling allows to have individual models for each business. These models can exist as an integrated model, or as 3 individual models, one for each filial. In this case, the data communication for the integrated multi-business model is defined by the Lagrangian relaxation methodology. Under a hierarchical conception, each subsidiary can be divided into sub-businesses that can be planned in a coordinate or integrate manner. Coordinating, when each individual model connects with another model to send its optimal decisions resulting from an isolated planning. Integrating, when all models are part of a holistic model that produces the real optimal decisions for the enterprise. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus of the company is obtained. This is how the human brain faces reality. Multiple models of reality, acting permanently in parallel, to make decisions. The algorithm that simulates the hypothalamus is assembled by OPTEX, using the models that traditionally make up a decision support system. Industry 4.0, intensive in data acquisition, extends the concept of real-time to any hierarchy of decision-making. Generating the concept of autonomous, real-time, distributed, optimization, in which multiple agents, distributed in the space, cooperate to solve an integral problem of the organization. An agent may be a country, a region, a business, an administrative department. The multiples models can run autonomously, activated by an exogenous event, for example, an earthquake, the failure of an industrial equipment, or by another model that requires processing their data. The artificial hypothalamus corresponds to a macro algorithm that coordinates the activation and solution of the models defined by the mathematical modeler. From the computational point of view, the models correspond to a set of microservices that solve problems and produce the required information, acting simultaneously and cooperatively. The concept of artificial hypothalamus can be applied to solve real-life problems from multiple points of view. In the diagram, the artificial hypothalamus coordinates models corresponding to the multiple problems faced by a company, organized from the point of view of its administrative functions. Another point of view is the spatial distribution of the problem. In this case, an artificial hypothalamus is presented for an agro-industrial company that has multiple facilities, farms, concentrated food factory, meat products factory, and stores in the food market. If an enterprise-wide optimization system, EWOS, is defined as the set of tables that make up the mathematical modeling database, a super application, that is, an application composed of several basic applications, can be defined by joining the tables of the two or more applications, ensuring that the integrity rules of relational information systems are met. The diagram shows the integration of applications for the management of public health problems, which corresponds to a regional planning problem, as experienced during the COVID-19 pandemic. To address the problem, HI developed EWOS Health, an application for pandemic management, built with OPTEX in 2021, and integrated it with EWOS HRPO, Holistic Regional Planning Optimization, built in 2006, implying that all models from the two EWOS can be used to build new models, through the mathematical modeling database, which uses a common data model for all models implemented in OPTEX, and/or through equations that integrate a single holistic model. OPTEX opens a new path for thinking about mathematical modeling. Joint problems is much easier than writing equations. That's the future of mathematical modeling, which has been used for 35 years by OPTEX, the optimization expert system. Do not program, every programmer's dream. Alfred North Whitehead affirmed, "Algebra is the intellectual instrument which has been created for rendering clear the quantitative aspects of the world." Thank you for your attention.